Welcome back, children. Now, there is an aspect of this lesson that has been omitted from your syllabus, but I thought I'd better talk about it now. This is about the law of radioactive decay. It's very important to know a couple of concepts like the half-life period and then the mean life period of a radioactive element. But for some reason, I think they've omitted it from your syllabus. But I want to talk about it anyway, so that you get an idea as to what they are, and they are very important concepts. Yeah? Let's say, so we are going to talk about the law of radioactive decay. The law of radioactive decay. Again, before we get into it, we'll talk about an example. Let's imagine that you have a village or a town where you have, say, 1,000 old people. Okay? So the population is 1,000. And out of this population, let us suppose that every year, say 10% of the population dies. It never happens, but I'm just, for simplicity's sake, let us suppose that 10% of the population dies every year. So, at the start of this year, let's suppose you have 1,000 people. And how many people would you have at the end of 1 year? So this is the village. So you start with 1,000. So 10% of the people die every year. It's too much. It happens. This is for argument's sake. This is to illustrate the concept. So you start with 1,000 and year 0. So you get 1,000. So at the end of 1 year, so how much should you get? 10% of 1,000 would be 100. So 900 would be around. Okay. So how many died? 100 people died. Okay. And at the end of the second year, how many would you have? Again, this is going to be 10% of 900, and you're going to get that is 90, right? 90 people will die, so you will get 810. Okay? So that would be the end of the second year. And then how many people would you have at the end of the third year? The third year, well, 10% again, 10% of 810 is going to be 81, so you get, this is going to be 9. And 2, 7. 729 would be the population at the end of the third year. So you start with 1,000 people, and then after 3 years, you end with 729 people, and every year, 10% of the population dies. So look at it. The number of people who die per year depends on the people you start with. If you start with 1,000 people, then the number of people who died in that year would be 100. If you start with 900 people, then the number of people who died in that year is 90. And if you start with 800 people, then the number of people who died in that year would be 81, and so on. So, the next year will be 72.9, 73. People will die the next year, and it will go on like this. Notice this. The number of people who die per year depends on the number of people who were in the beginning of the year. Okay, so I'll say that this is the number of people who die, right? That's going to be equal to delta y, right? This is the final initial. So delta y by delta t. In this case, it will be 1 year. Okay, delta t is equal to the 10%. I will call this as lambda. Okay, here it's a constant. So lambda into how many ever people were there at the time. Okay, I'll say this delta n. I'll probably put it this way. This delta n. So delta n is this. Delta n by delta t is equal to lambda n. Okay. So the other way of saying it is again, like if you do that, this delta n will be a negative number, right? The final is less than initial. So when people die, the later population is going to be less than the initial population. So final minus initial will be a negative number. So I'll say this. So delta n by delta t is equal to minus lambda n. So now if we want to do it more thoroughly, I'll say this n naught, this n1, and this would be n2, and then this would be n3. So now things become much more orderly. So delta n is n1 minus n0, so it will be minus 100. So delta t is first year minus 0, so it's going to be 1. So you're going to get minus 100. So this is what's going to happen here. So the point that we need to understand here is that the rate at which the people die depends on the initial population. If the initial population was 1,000, then this will be 100 per year. Initial population is 900, it will be 90. 810, 81. So I want you to understand that first. So I can say that delta n by delta t is proportional to n. I'll say this stuff, right? This minus delta n by delta t is proportional to n. The number at the beginning. And this is what it is. And the constant of proportionality will be lambda, and then you bring the negative sign there, and then you get this equation like that. So this is what I want you to understand. The opposite effect will happen when you deposit money in the bank. Suppose so this is death, okay, but this is decrease. What about increase? This is decrease, okay, and then money in the bank, increase. So first year, let us suppose you have 1,000 rupees, and then same 10%. So, and then you're going to have the end of the first year, you're going to have say 100 rupees more, so you get 1,100. So that's what will happen at the end of the first year. Then what will happen to the second year? So that will be 10% of this. You will have 110 rupees. So that will be, again, at the end of 2 years, you will have this what you have. It will go on like this. You see, it's an increment. And here also, if you have 1,000 rupees, then the amount of money per year is going to be 100. If it is 1,100, the amount of money per year is 110. And 121, then the amount of money per year would be 121. Okay, so this will be plus again 121. To add that 121, so at the end of third year, so how much would you have? So you have 1, 3, 3, 1. That's what we have. So here again, delta n, delta t, okay, is equal to lambda, same thing, into n. Whatever was there in the beginning of this period. Okay? the beginning of the period was 1100, then delta n by delta t is there, right? In 1 year, this is what you got. 110 is going to be equal to lambda, but this time it's going to be plus. So this is for growth, so this is for growth, and this is for decay. So if it is growth, then you will get a positive delta n by delta t. But if it is decay, then you will get a negative delta n by delta t. And notice that this is for a discrete happenings. Like what have we done here? We have tried to do it year on year. Okay, every year we're doing it. Like we're not counting the money in the middle of the year. We waited for 1 year, and then we see how much we had here, and and then I waited for 1 more year. Then we said we saw how much we had at the end of the second year, and it's like that. So we're doing it in discrete steps. But if you do it continuously, you don't have to wait for 1 year. What about the next microsecond, the next nanosecond? So what would be the change? Okay, you can do it too, right? So it is like we're bringing this delta t to 0. Instead of waiting for 1 year, so instead of doing it in a discrete fashion, this is discrete. What if we were to do it continuously? Again, this is discrete, and what is going to be continuous? If we were to do it continuously, then if you want to see what would be the rate of change of the population the very next instant, at any particular instant, then what happens is that this equation changes to this, right? Because this is average, it's kind of average for year. So if we do it instantaneously, then it's going to be limit, okay, delta t tends to 0, then delta n by delta t. And that is going to be again equal to dn by dt. That's the meaning of this, right? But that again is going to be minus lambda t. You know it, because at any instant, how much is going to die depends on, or how many are going to die depends on how many are there to start with. So this is not going to change. So this equation, continuous equation, becomes dn by dt becomes minus lambda. And here, the same idea, then you have the same limiting condition. So then dn by dt is equal to lambda. So this is for growth and this is for decay. That one is for increase and the other one is for decrease. One is for the increment, another one is for the decrement. Okay, I want you to understand this. You can see this in nature. In many situations, you will come across things like this. The rate at which things will change depends on how many you start with. Yeah, that's what I mean. If you start with a lot, then a lot of things will change. Okay? And if you start with a little, then little will change. So this phenomenon exists in nature. So in many situations in nature, you will come across this equation. So this is called as a differential equation. Okay, so just keep that in mind. If you understand this, if you understand what happens in decay and then in growth, then we're ready to talk about radioactive decay. If you take a certain amount of a radioactive element, okay, then it'll start decaying, and lot more will decay first, right? Because initially, let's suppose you have this amount of the substance, then a lot of things will decay, because like 10% or 5% of this is going to be a lot. Okay? Then because of this decay, that part, what would atoms or a nuclei that undergo this radioactive decay will become something else, and the remaining will be there. It's not that they will be gone completely, but then whatever has decayed would become something else. That is, I hope, understandable. It won't vanish, it will become something else. So when you look at it, a part of it would become, for example, like if you take one of the, let me take one of the examples here, okay. Let's say I have the uranium-238 example, okay. Uranium-238, after alpha particle emission, it becomes thorium. So if say 5% decays sometime, then 95% of it would be uranium and 5% of it would be thorium, and the alpha particles would have left, okay, gone somewhere. So you will have that there. Okay, so 95. So now at any point and every point you look at this, a part of it would be the original, and part of it would be the product, the daughter, the mother or the parent nuclei, and also the daughter nuclei would be present. So anyway, so there's a decay that is happening. So once like that a certain percentage is gone, then whatever decay that is going to happen will depend on whatever uranium is remaining. To start with, all of it was uranium. So many decayed. And when you look at it at a later point in time, the number of uranium nuclei would be less than the number of uranium nuclei when you started the whole thing. So when you come back again for the second time, then the number of uranium nuclei that would have undergone this change would be less, right? Just as we saw in the case of the village containing 1,000 people, and who were 10% of which were dying every year. So initially started with 1,000, then 10% died, then you have 900. The next year when you come back, you get 810. So only 90 would have died, not 100. Only the first year 100 will die. The second year only 90 will die. And the third year only 81 will die. So that's happening. So the radioactive decay is a process like that. And we said that the decay rate, dN by dt, here we said, okay, if it is decay, we said dN by dt is equal to minus lambda, this constant rate at which it's going to decay, lambda into the initial population at any point. I mean, if you're when you started, you'll have certain number. And after 1 year, okay, 1,000 has become 900. So for the next year, 900 is the beginning. So 900, 90 will be gone. So we'll be left with 810. And then for the next year, like 810 would be the beginning. So 1,000, 900, and 810. So those are going to be these ends. And at every point in time, this rate at which they die, that the decay takes place, depends on the initial population at that time. Okay? So that is what this equation tells you. Well, so this is a differential equation. I hope this has been taught to you in mathematics. But even then, even otherwise, you can still do something. You can understand this. So because it's a decay process, you have minus lambda. And this lambda is called as a decay constant. The rate at which the decay takes place, constant decay, constant. Like the 10%, whatever we talked about. This one. So it's a decay constant there. So what I'm going to do, now I'm going to rearrange things now. So I'm in differential equations, it's called as the variable separable form. Even if you don't know it, just follow what I'm going to do. So I'm going to have dn here, and I'll bring n here down. And this is equal to minus lambda dt. So dn by n, then minus lambda into dt. So I said I'm going to start from a particular time. I'll call it as the time is 0 to t. So I'll start the time at which I start. Okay. So I call as time t0 is going to be equal to 0 and stop. Okay, and then t1, then t2 is going to be some t. Okay? That is there. And when at t1, I'll say my n was equal to n0 initially. At the time of observation, I start observing. So at that time, I see a certain number of nuclei. It could be, say, 900 or 810, anything, or even 1000. But the time at which I start observing it. So that is n0. Okay. So how do I solve this? Then I can integrate it. If I see integrate this, and let's see what I'm going to write. I'm going to integrate it from, okay, let's say an initial. Okay, and then n final. It's going to be n. This again is initial, or I'll say this is n1, or this could be n2. But n1 is n0, this is n is n. Okay. So what I'm going to do, this will be, I'm going to go from n0 initial to some value n. See, if I observe it after some time, then initially it was n0, and after some time it will be n. Clearly, this n will be smaller than n0. Because I start, now I see maybe it's 1000, and I'll come back after some time and look at it, I have only 900. So I go from 1000 to 900, n0 to n. Here I go from, say, 0 to some time t. That's the thing. So let me take a dn by n, that is dx by x, right? It's ln x. So ln x, or log, the natural log, right? I don't know how you write it. It's going to be log n to the base e. That is it. The limits will be n0 n. So here this is going to be minus lambda I can take out, but this is simply going to be t. So t, and this is going to be, the limits are going to be 0 to t. Okay, I could have put t1, t, whatever, this is t. So this gives me log n to the base e minus log n0 to the base e, and that is equal to minus lambda into t. So it's a delta t, okay? The difference between those two terms is t. Well, what can I do now? I can do this, I can bring them together. See, the log e to the base, log to the base e, I'm going to write as ln ln. It simplifies a lot of things. So this is going to be ln n minus ln n0 equal to minus lambda t, and this will become ln n by n0 is equal to minus lambda t. Okay. So this log to the base e, n by n0 is equal to minus lambda t. Then if I remove the log, so what would I get? I'm going to get n by n0 is equal to e to the power minus lambda t. So you know that, right? Okay, so the same thing as this log, like this. If it is log a to the base b is equal to x, then a is equal to b to the power x. That's the formula you're using. So e to, that's what I use. So now this gives you n is equal to n0 e to the power minus lambda t. So this is called as the active equation, the law of radioactive decay. You can see that. Okay, so if I know the initial population, and if I know the decay constant lambda, then I will know after, say, any amount of time how many nuclei will be left after the decay has taken place. And clearly, this amount of the parent nuclei that will be left after time t. Okay. And if you know this, then I will also be able to know how many have decayed, right? That's going to be n. So n naught minus n is the number of nuclei which have decayed already, right? Because you started with n naught this way. You started with n naught. Now you have some n. So how many nuclei have decayed? Simply n naught minus n. But what is n? N is this n naught e power minus lambda t. So I can do the 2 here, right? N naught minus n naught to e to the power minus lambda t. So that would be n naught into 1 minus e to the power minus lambda t. So this is the number decayed, and this is the number left with. You are left with this number. Now, so many nuclei would be left with, and so many nuclei have decayed. And n naught is your initial position. It's like this. If you had started with 1,000 people, if 100 people died, then 900 people will be living. So this is 900 people living. You started with 1,000 people, then you are left with 900 people. And how many died? 100 died. So that's what it is. Okay. So but this is very important. This is only for understanding. This is very important. This n is equal to n naught into e to the power minus lambda t is called as the law of radioactive decay. So at any point in time, you would know the number of nuclei left when you started with n naught using this equation. I hope this is clear to you. So you know this equation now. N is equal to n naught to e to the power minus lambda t. This is the number of nuclei when you started at the beginning, and t is the time that is elapsed. Okay, and lambda is the decay constant, and n is the number left, the undecayed number of nuclei. Okay, that's what it is. So if you were to draw a picture, draw a graph with time, then this is what I will get. Okay, and so time is like this, and this is going to be my n at any point in time. Okay, so at time is equal to 0, then I'll have, that is I'll start observing, right? So I'll start here, that's why n naught. And as time increases, you see the n comes down, comes down, comes down, comes down. So you'll have a graph like this. Like that. So notice here, the dn by dt at any and every point here, see that slope, that will give you the decay rate. How much it decays. The decay rate will be given by dn by dt. So if I do a dn by dt, what I'm going to get now here. So what is n? N is equal to n naught e to the power minus lambda t. So if I do dn by dt, that is going to be n naught will leave, then this is going to be e power minus lambda t into minus lambda. Correct? This is what it is. So this again gives you, what is this? N naught into minus lambda is n. So you get minus lambda into n. So dn by dt is minus lambda to n. Okay. So this dn by dt is also called as the decay rate. The decay rate, a rate of decay. And we know this anyway. This is what we started with, right? We said dn by dt is equal to minus lambda n. So that's what it is. So the slope here, gives you the rate at which dn by dt is here, and when n is here, then you have a different slope, and here you have a different slope. It's like that. So the rate at which the number of nuclei which decay per second depends on the initial the initial nuclei at that time. I mean, at this time, this is the initial nuclei. So after a little amount of time, then this will be this will be the rate of decay. This will be the rate of decay. I hope you understand this. So it's a continuous decay. You're not doing it year after year, as we did in the case of the village population. This is you're continuously decaying. So at this point, this will be the rate of decay. dn by dt will be this number. At this point, this number. This point with this number. The slope. That is also changing. So clearly, that also is coming down because the amount of substance available for it to decay, then it's getting reduced. I hope you understand this. Okay. So an important concept of this is the half-life period. So what it means is that I start with n naught. I start with n naught here, and then how long will it take for me to have this n naught reduced to say n naught by 2? Okay. So I have so many nuclei now, one box full of nuclei. How long would it take for me to have only half of this box available? The remaining half would have decayed already. So what is the time it will take me to do that? So that is called as the half-life period. Okay. So the half-life period is called as T half. So I'll say half-life period. So that is the time you take to go from, or they do it as T half. Time you take to go from n naught to n naught by 2. What is the time you take to do this? That's the half-life period. Well, I'll say we start with n naught. So I start with n naught, but now the n has to be n naught by 2. So what is the time here? That's what I should see. So you know this equation: n is equal to n naught, n is equal to n naught e power minus lambda t. But half-life period will result in this n being n naught by 2, half of it. Yeah, must be equal to n naught e power minus lambda, and this time is going to be called as t half, half-life period. What is that time? So clearly, n naught and n naught will cancel. So if you bring it here, you take it there. So you know that e power lambda t half, I'm bringing it here, equal to 2. Take it there. Okay. So what is t half now? So if I take log the whole thing, log to the base e, then I get lambda t half is equal to ln 2. So that gives me t half, which is half-life period, that is equal to ln 2 by lambda, or in this case log 2 to the base e by lambda. That's what it is. So I say this ln 2, it's log 2 to the base e by lambda. Okay. So this is a very important concept. So it tells you how long does an element or a radioactive element take to become half its original amount. So for that you just need the decay constant, lambda. If you know lambda, depending on lambda, this ln 2 is constant. Okay, it's just some number, right? This number is not going to change, ln 2. But then depending on the element, lambda could be different, and depending on that, you can find out how many days or how many years or how many millennia it will take for for particular amount to become half, and that depends purely on the decay constant. So ln2 by lambda. This is the half-life period. It's what is called as the half-life period. Okay, and the other thing said this decay rate dn by dt. They have a different name for it. We call it as R. So this dn by dt, it's like some kind of a modulus, okay? So you get a positive number. So that's R, that is simply lambda n. Okay. So that is radiative decay rate. Instead of negative number, you're going to have a positive number and you call it as R. That's it. And then this dn by dt is like you have a unit for it. That's called becquerel. It's named after Henry Becquerel. So this is the unit for this is decay rate is becquerel. Okay, that's a unit. So what it means is that 1 decay per second is 1 becquerel. Okay, so 1 disintegration per second is equal to becquerel is equal to 1 decay, 1 nucleus per second. So there are 10 nuclei per second and it's 10 becquerel. So clearly it's a very small number. So you use another number called as Curie, named after again Mary Curie, considered to be the most famous woman scientist. She was both a physicist and also a chemist, and she is the first person to get 2 Nobel Prizes, one for physics and one for chemistry. So that is 1 Curie. 1 Curie is equal to 3.7 into 10 to the power 10 decay per second. Okay. It is 37 billion decays per second. That's what I will say. Or you can say it's becquerels. Okay, 3.7 into 10 to the power 10 is becquerels. The way BQ, it's becquerel. So this is 1 Curie. Okay, so this is about the half-life period and also the rate of decay, dn by dt. The unit for rate of decay is becquerel, or 1 decay per second. And it's a very small number, clearly, because like if you take any chunk of material, you have trillions of atoms, so many will try to decay at the same time. It's a very small number, so you're going to use this number, which is Curie. So where 1 Curie is equal to 3.7 into 10 power 10 decay per second, or 3.7 10 power 10 becquerel. Okay, so hope this is clear to you. Okay, now we know what the half-life period for an element is, radioactive element is. So it is T half, let's say T half is given by ln 2 by lambda. But ln 2 is log 2 to the base e is 0.693 by lambda. So this is what half-life period is. The lambda depends on the nucleus. Anyway, so this is one thing. See, it doesn't tell you what the average life of a nucleus is. Okay, so you start with so many, so 1000 nuclei, example, and maybe like after some time you come and see, and half of they're gone after the half-life period. Okay. But you will never know, what does it mean? How long will an average nucleus will live? Okay, see, clearly. Some nuclei have undergone radioactivity immediately, right? So that is why you got this. So first, some nuclei will start decaying, and then after some time, some other. So not everything is going to die at the same time. Okay, that's not going to happen. Some nuclei will die now, and some nuclei will die a little later, and some of the nuclei will die a little later than that. So that's how it is. So like when you come back and look at it after the TF time, the half-life period, then half of this is gone and half of this material will remain. But this doesn't tell you for how long a nucleus will live on the average. Doesn't tell you at all. I mean, clearly, if you look at this picture, let's see, graph. What is the graph? You see, this is T and this is N. You start at N0 and then the graph goes like this, right? So this graph is N is equal to N0 to the power minus lambda T. You note here, you don't have the same N0 here. Like the N0 is reducing, the number is reducing, but the notice some nuclei could live for a really long time. Okay, for infinite time, some could live theoretically. Think about it. Okay. In the same material, some of them die quickly. You see, from here to here, immediately some nuclei have died, right? And that is why you get this. From N0 to come down. Some have died immediately. But then some nuclei can live forever. Theoretically, if you look at this graph, for infinite time. So, the life of any specific nucleus is uncertain. We don't know. When we can't take a single atom and then say this nucleus will die in so many days or so many years. You can't even say that. So, how do you find the average life, the mean life of a nucleus? You can say, take a nucleus and then say, okay, on the average, this nucleus can live for so many years, or so many days, so many seconds. How do you find the mean life? How do you find the mean life of people, human beings? Well, you take a person, if you take a village, somebody can die at the age of 90, somebody can die at the age of 80, and most people can die at the age of 70, and sometimes even children die. 5-year-old kids and 10-year-old kids, they die. So you don't know, like you can't say how long any specific human will live. But on the average, you can say, when you say the life expectancy of Indians is about 70 plus years, then what you're saying is, when a child is born, you can expect the child to live up till say 70, 75. In the Indian conditions, yeah, I can expect the child to live till 70, 75. On the average, will all the children live to be 75? No. Some may, as I said, may die young. Some may die at 40. Some may die at my age, and somebody else may live longer than even 75. Some people may die at 94. Some people may even cross 100. But on the average, what can you expect? You take any human being and then say, okay, any Indian. The Indian average is 75 years, right? 70 to 75 years. I'm not sure what number exactly is, but somewhere around 70 to 75. So you take randomly any person and then say, yeah, this person, I can expect him to live till 75. Will he live till 75? No. I mean, you don't know. He may die early. He may live longer than 75. You don't know. But on the average, if I make that prediction on, say, 100 people, a good number of people will meet my criterion. So that's what it is. Okay. So I'm trying to find the mean life of a nucleus, the average life of a nucleus. The half-life period doesn't give me that information. It just tells me how long it takes for this material to become half its original amount. That's half-life period. And then if I start with this, maybe it takes 10 years for it to become half. And then I start with half, and for that half to become half of it, which is quarter, then again another 10 years. And then for that quarter to become half of that quarter, that is 1/8, will take another 10 years. So the half-life period is always about what you start with. If you start with 1 kg, then it will probably take 10 years for it to become half kg. If you start with 10 kg, then it will take 10 years for it to become 5 kg. Okay, that is half-life. It all depends on how much you start with, whatever amount that be. From that amount, for you to go to half that amount, what's the time it takes? That is half-life period. But here, you're talking about mean life period, which is different, which is the average time any particular nucleus can live. Okay, so that is, will every nucleus do that? No, that's not the case. On the average, if you look at a random nucleus, I can say, well, it can live up till this time. Will it live? That's mean life. Okay, I'm talking about mean life, but it gives me an idea as to how long I can expect each nucleus to live. So how do I do that? So how do I take the average, for example? Like we've done this already in your electricity lessons. So if you have a curve, then you find the area under the curve, and you find the area under the curve, and if you divide it by this time, then I have this value, and find the area under the curve, and if you divide this time, divide this by this value, then I will get this thing. So what I mean by that is it's like this. I have a curve like this, and what I'll do, I can find the area, and if I divide this area by this value, then I'll get this constant, right? So what it means is that this value multiplied, this value multiplied by this rectangle has the same area, the red rectangle has the same area as the blue curve. Or I can find this and I can do it this way also, right? For example, do something like this. Green. So this rectangle also can have the same area as this. So what I'm doing here, in this case, in the red case, I take this area, divide it by the x-axis, then I get the y-axis value. In this case, what I do, I find the area, divide it by the y-axis value, then I get the x-axis value. Okay, so that is what I'm going to do here. First, I will find the area. So this is the equation. How do you find the area of this curve? So the area of this curve is going to be equal to integral, okay, from n naught into e to the power minus lambda t, that is n value, into dt. Okay. I'm going to integrate from 0 to say infinity. 0 to infinity. It's going to go on and on and on. It gets smaller and smaller and smaller, but then it can really go on and on and on. So when you do that, what's the area I get? What is the area of this curve? That will give me n naught e to the power minus lambda t by minus lambda 0 to infinity. That's what I get. Well, start substituting. Now I get n naught to, when I put infinity here, t is equal to infinity, e power minus infinity. E power minus infinity is 0, so that will become 0. Then minus of this one, e to the power minus lambda into 0, t0, then minus lambda. Okay. So this will be e power 0, it's going to be 1, minus lambda minus with plus, right? So I'm going to get n naught by lambda. So that's the area of this curve. The area of this curve is n naught by lambda. I found the area of this curve. But what I'm going to do now, I'm going to find this time. I want the time, the mean time, right? So I'm going to divide this area by n naught. We divide that by area n naught, then you will notice I'm going to get this thing. So this will be my tau, which is the mean life, mean time. Take this area, divide this by this, and then I will get this value. So that's the average. Yes? So what is the average? What is the average time? Take this curve, divide it by this. Remember, what did you get the average value, the power? You integrated, you found the area, and then you divided by the x-axis. Then you got the y-axis. Now what I'm going to do, I find the area, I'm going to divide it by the y-axis, then I will get the x-axis. So that's the average time. This was average. If I divided it by time, then I would have got the average number. It doesn't make any sense here because the time is infinity, so it will be 0, whatever we had. I will not do that. I am trying to find this. So I will take this area, divide that by n0, then I will get this tau. So that's what I will do here. So this is area. So average time, mean time, okay, let's say mean time tau, or mean life. Mean life, okay, it's called tau. It's going to be equal to this integral divided by n0, right? This is going to be a by n0. This is equal to integral 0 to infinity n0 e to the power minus lambda t dt by 1 by n0. Correct. I hope this rings a bell and you are able to connect it with your electricity chapter. But in this case, you are dividing the area by the y-axis, not by the x-axis, because you want to find the x-axis value. In electricity, you divided it by the x-axis because you want to find the y-axis value. But this area is the same as this area. That's what I'm trying to drive it. So now 2 is equal to what I got here. This area is n0 by lambda, and divided by n0 goes, so it's going to be 1 by lambda. So tau, the mean life is simply 1 by lambda. If you know the decay constant lambda, then this gives you the mean life. Okay, so this is the time you can expect any particular nucleus to live on the average. So that's why it's mean life. So this is TF. There are two things now we have discussed. Okay, I'll do it here. TF, that is the half-life period, and then tau, this is half-life period. This is the mean life period. Well, you know what is tau? TF is ln 2 by lambda. But you know 1 by lambda is tau. So what is the relationship? So TF is equal to tau into ln 2. These two are related like that. So if you know the decay constant lambda, then 1 by lambda gives you the mean life period for a nucleus, and ln 2 by lambda or tau into ln 2 gives you the half-life period for the nucleus, for the atom, the amount of substance there. Okay, I hope this is clear to you. Okay, we'll do an example problem. We'll do example 13.4. The half-life of uranium-238 undergoing alpha decay is 4.5 into 10 power 9 years. See, it is 4.5 billion years. So what does it mean? It's roughly the life of the Earth. Okay, the Earth is there for about 4.3 billion years. So if you think about it, whatever uranium you had on the Earth in the beginning when it was formed, the Earth was formed, now you got half of it. That's what it is. So it has taken so long for uranium to become half. So it takes. It's not when you say radioactive. So some elements are very, very, very fast. For example, carbon. So it's the radioactivity is it's too much. Like it can be used for carbon dating and stuff. Okay, but uranium 238, for example, like left to itself, it's pretty stable. Think about it. It takes 4.5 billion years for uranium 238 to become half of it. So I want you to understand that is different from uranium 236. okay, which will immediately, that's very unstable. But this is different. So uranium-238. So the point is, not all isotopes of a particular material are dangerous, or they undergo radioactivity at a very fast rate. It's not like that. Some isotopes undergo fast decay, and some other isotopes undergo slow decay, and some rarely at all. It's like that. Okay. So carbon-14 and carbon-12. Carbon-12 is a very stable thing. It will be there almost forever. But carbon-14 can undergo radioactivity pretty quickly. So not all isotopes do the same thing. I just wanted to remember that. And not all radioactive isotopes undergo decay at the same rate for the same element. Okay, keep that in mind. So this is the point. Okay, so the half-life period of uranium-238 undergoing alpha decay is 4.5 billion years. What is the activity of 1 gram sample of uranium-238? The activity. Activity means the rate of decay, which is R. That is activity. That's what it is. Activity means the rate of decay, which is dN by dt. Which is dN by dt. Okay, that positive number. Okay. Let's see. So the half-life period is given. So T half is 4.5 into 10 power 9 years. If I convert that into seconds, this is what I get. 1.42 into 10 power 17 seconds. So 4.5 into 10 power 9 years equals 1.4 into 10 power 17 seconds. Okay, that is fine. So what is asked? What is the activity of 1 gram sample? What is the rate of decay of 1 gram sample? So you know that the rate depends on the amount, right? Because dN by dt is equal to lambda minus lambda into n, whatever substance at that point in time. So they talk about 1 gram sample. You got 1 gram now. So what is the rate of decay? What is the activity? How many nuclei will decay per second? That's it. So let's say in 1 gram, you know this, right? In 1 gram of uranium-92 238, okay, how many atoms are there? Well, how many atoms? What is your N naught? That's the question. Well, you know, in 238 grams, you have 6.022 into 10 power 23. Okay, I'll get a number of atoms, right? Are there. Now, how many in 1 gram? So 1 gram is equal to same 6.022 into 10 power 23 is by 238 into. So yeah, that's it. Okay, so many atoms are there, and if you do that, you're going to get 25.3 into 10 power 20 atoms. Okay, so that is 1 gram. You got, so this is your N naught. So your N naught is going to be 2.53 10 power 21. So when you have 1 gram of uranium-238, you have so many atoms in it. Okay. Now what is asked? What is the activity? What is the activity? dN by dt, right? So you know dN by dt is equal to lambda n. Yeah, that's R. So this, right? So that's activity is lambda n. But how do you find lambda here? Well, you know TF, what is TF? So TF is equal to ln 2 by lambda, which is equal to 0.693 by lambda. You know TF is given, TF is this. So this gives you lambda is equal to 0.693 by TF, that is 1.42 into 10 to the power 17. Okay. So you get some value for that. Okay, you get some value for that. But now what is R? Rate is lambda into n. So this is going to be 0.693 divided by 1.42 10 to the power 17 lambda into what is n, which is n naught, right, at this point in time. Okay, so it's 2.53 into 10 to the power 21. I'll call this as n at that point in time, 10 to the power 21. So if I do that, I get my rate is 1.23 into 10 to the power 4 becquerel. That is so many atoms per second. That's what it is, right? So this is what it is. This is how you do it. And if you want to convert it into curie, you can do that too, but you see it's a very small number. You get a very small curie. So this is what it is. So when you have 1 gram of uranium-238, then you can expect 1.23 in 10 to the power 4 decays per second. And it will take another 4.5 billion years for that 1 gram to become half gram. Okay? So that's how it is done. Hope you understand this. And the other thing is, example 13.5, tritium has a half-life of 12.5 years undergoing beta decay. What fraction of a sample of pure tritium will remain undecayed after 25 years? Okay. So it's tritium, which is one of the isotopes of hydrogen, is half-life of just 12.5 years. Remember, uranium-238 has 4.5 billion years, but tritium will become half in 12.5 years. So what fraction of a sample of pure tritium will remain undecayed after 25 years? Well, that's again easy. I'll do it here. Okay. I'll do it here. So TF is 12.5 years. So if you have a certain amount of material now, after 12.5 years it will become half. And so then whatever mass you had, after 1 TF it will become m by 2. That's a new mass. Then that m by 2, then another 3.5 will become half of that. Now it will become m by 4. So this is 12.5, this is 12.5, total 25 years. After 25 years, then how much will you have? You will only have 1/4 of it. So only 25% of the original amount will remain. If you have 1 gram of tritium, after 25 years, you will have only 0.25 grams. So 0.75 grams would have decayed. Okay, so only 25% of that, of the original material would remain. So hope you understand this. For some reason this has not been mentioned in your syllabus, but I thought you had better know this. Okay? It will give you, it's a fascinating idea. It tells you a lot about radioactive decay, and I feel that the law of radioactive decay must be there. I don't know why they removed it, but wonderful idea.